Lever system. In hydraulic system, there is a lot of application of lever system. There are three types of lever system, as you know. First class lever. It's kind of like a seesaw. An example would be seesaw, like that, opening mouth. Something like that. So the first class system, lever system, the way it looks is like this in a hydraulic situation. So this is the pivot point. And imagine that we have a load that we're trying to pull up, load, or we can say F load. And then the cylinder here is trying to push down, F cylinder. Push down. Now, if this length is L1 and this length is L2, and imagine that this is at an angle theta, this is the angle theta. So we can develop a formula for this lever system if we take moment with respect to the pivot point. So summation of moment, anti-clockwise moment, all moments is equal to 0. So if we do that, then for this F cylinder load with respect to this pivot point, it will do an anti-clockwise moment, which we usually use positive sign for that. So F cylinder anti-clockwise moment times the distance. Now to calculate moment, we need to find the shortest distance, in this case this one. So if this is theta, this will also be theta. So if this part is L1, then this shortest distance will be L1 cosine theta, like that. And then with respect to this point, the load will make a clockwise moment, which is negative. So minus F load, and then the distance, shortest distance will be L2 cosine theta, and that's all we have, equal to 0. Then we can calculate the F cylinder load, how strong cylinder or how much load we need to produce by the cylinder. Simply just solve for F cylinder, which will be L2 by L1 times F load. So using a first class lever, we really don't gain much advantage of levers. Is kind of neutral. So the first class lever is neutral because if these both lengths are same, L1, L2, they don't provide any advantage. So I would like to call that neutral in terms of mechanical advantage. Neutral with respect to mechanical. Oh, sorry about that. With respect to mechanical mechanical advantage. We did, but so we don't get mass force advantage or mechanical advantage from the first class lever. Let's see the second class lever. I think I have enough space here. So I'm gonna use that. So second class lever looks something like this. So let me show you this. The cylinder is still here, but it is applying a force upward. And then the pivot point is still in the middle. So that's the pivot. And then the load, sorry, that's the load actually. That's the F load, and there is the pivot point. So that's the pivot. If we use the same notation, L1 for this distance, L2 for this distance, and this angle is theta, so we can do a similar moment with respect to the pivot point, and all moment is equal to 0. You could set that equation. So with respect to this pivot point, moment due to the load will be EF load times the distance. So that would be a anti-clockwise. So that's positive, plus F load, and then the distance is L2 times cosine theta, shortest distance. So that's positive. And this F cylinder will be a negative moment with respect to that point. So that's negative F cylinder, then L1 plus L2 times cosine theta, and all of this is equal to 0. If we solve for F cylinder, we'll get L2 by L1 plus L2 times F load. If you look at this first class lever and compare the second class, we get, this is the second class lever, this is the first class lever. We get a mechanical advantage here. So whatever L1, L2 you use, we get, and whatever load we are trying to lift using, we have to use a small size cylinder compared to the load. And here, so this is actually mechanically advantageous, not really neutral. Mechanically advantageous. The third class lever, it looks like if we have a load here, F load, and then the cylinder is in the middle, we have F cylinder, and then this is the pivot point. So pivot point. Again, this is L1, L2, and the angle is theta. Now, if you take moment with respect to summation of moment with respect to the pivot point, all moment anti-clockwise 0, anti-clockwise positive. So for the F load, we get a positive moment because it's going to make anti-clockwise moment with respect to this point. So F load times the momentum, the shortest distance, is cosine theta. And then minus the cylinder will make a clockwise, cylinder load will make a clockwise moment, minus F cylinder L2 cosine theta, all of this equal to 0. If we solve for F cylinder, the load that the cylinder has to produce is gonna look like L1 plus L2 divided by L2 F load. So cylinder has to produce more load. This is actually mechanically disadvantageous, so we need a bigger cylinder to lift same amount of load. Advantageous. Now, you may be asking, why do we use that? It depends. We sometimes need a disadvantaged cylinder. Think about our elbow. The elbow joint is basically a third class lever, which is not as strong, because if it's too strong, then a lot of times we're going to break our bones because of this. So second class lever example would be the ankle joint. where we need to lift, we need to carry our body. So same thing for the hydraulic system. If we may need something weaker in some situation, we may need something stronger. Depending on the application, all these three types of levers are used in the hydraulic system. Now, there's one more thing we need to talk about. If we have a cylinder like this, imagine a cylinder like this is pivoted right here. So if the cylinder is, pushing or pulling a load like this, let's think about the first class lever example. This is the load. This is the pivot point. So when this cylinder, for example, pulling down, if this has to rotate because this is a solid cylinder, it cannot just go down without rotating. So it may happen that sometimes the cylinder may just take a position like this at an angle. So, just because of facilitating this rotation, because if it's pulling down, then it cannot just have straight up and down. It has to kind of go. So oftentimes it is not, it could be mounted as a fixed, but oftentimes it is mounted in a way so cylinder can rotate and facilitate some movement. If this rotated angle is phi, then the force that cylinder apply, at the pulling force along the line of this cylinder will be basically F cylinder cosine phi instead of just the F cylinder. So all the equation we have seen for the first class lever, we have seen that first class, the equation was something like F cylinder time is equal to L2 by L1 and then F load. Because this cylinder force is not anymore just F cylinder, because it's acting at an angle, it is kind of losing some force. So it's using some levers. So if we have F cylinder cosine phi, then it goes here, cosine phi. So that equation 1 become, I would like to say 1A. Equation for the second class lever becomes F cylinder is equal to L2 by L1 plus L2 only, and now because it's acting at an angle, cosine phi, and then the F load. Now be careful not to confuse this the lever angle theta with phi. Phi is the cylinder angle and theta is the lever angle. So if we change this third class lever equation, it's gonna look like F cylinder is equal to L1 plus L2 divided by L2 cosine phi F load. So that would be in case if we have a cylinder situation like this. Now, most of the time when we solve a problem, we use this basic moment application theory. We take the moment with respect to the pivot. That's how we solve the problem. I feel more comfortable taking the moments and solving the problem instead of directly using the formulas. These formulas or explanation is just for you to understand the three classes of lever and what's the advantage, disadvantage of that. But when we solve problems, we typically apply moments in the pivot point and then solve it manually instead of directly using the formulas.